A very good morning, friends. I once again welcome you all for the third session of the first chapter, that is combinational logic circuits. So, here in this session, we shall discuss how to implement the logic gates functionalities using multiplexers. So, first we shall discuss how to implement the functionality of logic gates using 4:1 mux, and in the later session we will discuss how to implement the same functionalities using 2:1 muxes. The first thing that we should note down here is we will follow two methods here. That is one method that is used for the 4:1 mux, and we will use the different method if we are using 2:1 muxes. Why these two are different? Because first we have to see here whether the number of select lines are equal to the number of inputs of the logic gates or not. So if you consider the case of 4:1 mux, as we know that in 4:1 mux we have two select lines, and the number of inputs of all logic gates except not all are 2 only. Since the number of inputs of the gates are equal to the number of select lines, we follow the first method, which will be discussed now. So while implementing the same functionality using 2:1 muxes, as we know that in 2:1 mux we have only one select line, but all logic gates they have two inputs. There we use some other method which is nothing but map entered variable method, which will be discussed in the later session. First we shall see how to implement using 4:1 muxes. So here, as we know that the number of select lines are 2 and the number of inputs of all logic gates except NOT gate are also 2. So here the numbers of inputs of the gates and the number of select lines of the mux are equal. We can directly map these inputs with the select line contents here. And we should again, and if you see the truth table of uh, any logic gate except NOT gate, so with two inputs, since with two inputs we can have four different combinations, this will result four different outputs. And if you count the number of data inputs of 4:1 muxes, they are again 4. So one more input is there, that is enable is there, so which is always connected to VCC, so that this logic system is enabled always. And if you count the number of output of logic gates, there are 4 outputs are there, and we have 4 inputs in the 4:1 muxes. Means the mapping is done in this way. The inputs of the logic gates are directly mapped with the select line contents of the 4:1 mux, and the 4 different outputs are directly mapped in a sequence with the 4 inputs of the 4:1 muxes. So as we know that this is an AND gate symbol and this is the truth table with 0 0. So we can easily say that, so whenever the inputs are 1 1, the output will be 1. In all other cases it is 0. Or you can say AND is 1 when both are 1, means when both inputs are 1. In all other rest cases it is 0. Okay, so since now the count of inputs of the gate is equal to the count of select lines here of the 4:1 mux, I have directly mapped the A and B with S1 and S0 here. The first step is over, and now the next step is I have to map the 4 different outputs with the 4 inputs of the 4:1 mux in a sequence. In the sense, so as A and B are 0 0 here, so since A and B are mapped with S1 and S0, So since these two are 0 0 means 0 0 means it will select D naught content. With 0 0 I have an output 0, so means this 0 is directly mapped with D naught. Similarly, for the next case, again it is resulting 0, which is mapped with D1. So this is mapped with D0, and this one is mapped with D1, and the third output is mapped with D2, and the fourth output is mapped with D3. So accordingly, if the output is 0 means that should be connected to ground, and if the output is 1 means that should be connected to VCC. As we can see here, since the outputs of the gates are mapped with the inputs of the 4:1 muxes, D0, D1, D2, all are zeros here, means they should be connected to ground. Whereas D3, its content is 1, so that's why it is connected to VCC. Let's see whether this 4:1 mux works as an AND gate or not. In first case, as S1 and S0 are both are 0 0, with 0 0 it will select the first input line, that is D0, so which is connected to ground, and its information is routed to the output Y, means with 0 0 I am getting a value 0. With select line content 0 1, again D1 is selected, which is again connected to ground only, so the same 0 will appear at output line Y. With 1 0, D2 is selected, which is again connected to ground, so it will result an output 0. With the last combination 1 1 of select lines, D3 is selected, which is connected to VCC, means 1 is routed to the output line Y. So now if you compare the AND gate truth table with the, this is the AND gate truth table with the 4:1 mux truth table, both are replicas of each other. I can say I have successfully implemented the functionality of AND gate using 4:1 mux. Okay. Next we shall see about the OR gate. So in OR gate also we have two inputs, means if you compare the number of inputs of the gate with the number of select lines, both are equal here, means I can directly map these two inputs of the gates with the select line contents of the 4:1 mux. And if you write the truth table, so as we know that OR is 0 whenever both inputs are 0. In all other rest cases it is 1. So that is for 0 0 it is 0, 0 1 it is 1, 1 0 it is 1, and for 1 1 again it is 1. And if you represent it in a min term representation for the decimal combinations 1 2 and 3, for 1 2 and 3 the output is 1. This is the min term representation. So as we know that, so these outputs are mapped with the inputs of the 4:1 muxes, because the number of outputs are equal to the number of inputs of the 4:1 muxes. For the first combination, so it is 0, means D0 is connected to ground. For next combination, next three combinations, successive combination, these are 1, means D1, D2 and D3 are connected to VCC, and as usual enable is always connected to VCC. And if you verify the functionality of 4:1 muxes as per the input combinations here, we will get the same functionality of the OR gate. Similarly for NAND gate, as we know from the truth table, this is inverse of AND gate, means for 1 1 combination it is 0, for other combination it is 1. And if you represent it in a min term representation, For the decimal combination 0, 1 and 2, the output is 1. The inputs of the gates are mapped with the select line contents, means S1 is mapped with A and S0 is mapped with B, and these 4 outputs are mapped with the 4 inputs of the 4:1 muxes in a sequence. The first 3 outputs are 1, means the first 3 inputs of the 4:1 muxes are connected to VCC, and the last combination, that is which will result 0, means D3 is connected to ground. NOR gate, again this is inverse of OR gate. So here for input combination 0 0 it is 1, for rest other combination it is 0. This is inverse of OR gate. So here again I have mapped the 2 inputs of the NOR gate with the 2 select lines. S1 is mapped with A and S0 is mapped with B, and the outputs of the OR gates are mapped with the inputs of the 4:1 muxes. The first output is 1, so that's why D0 is connected to VCC, and the rest outputs are 0. The rest inputs of the 4:1 muxes are connected to ground. Similarly, XOR gate, XOR will be 1 whenever inputs are different, in the sense whenever inputs are different in the sense whenever input combinations are 0 1 or 1 0, the output will be 1. For other cases it is 0. Again here the inputs A and B are mapped with S1 and S0, and the outputs 0 1 1 0 are mapped with the inputs of the 4:1 muxes. The first and the fourth outputs are 0, means D0 and D3 are connected to ground. And the middle two are 1, means the D1 and D2 are connected to VCC. This is about the XOR gate. And this is XNOR gate, which is reverse of XOR gate. XOR is 1 whenever both are same, in the sense whenever both inputs are same, in the sense whenever both are 0 0 or whenever both are 1 1, the output is 1. For other cases it is 0. Here inputs are mapped with the select lines and the outputs are mapped with the inputs of the 4:1 muxes. You can verify the functionality as per the truth table. And the last one is the NOT gate. So in NOT gate, this is a special condition here, because the number of inputs of the NOT gate is only 1, whereas the number of select lines of the 4:1 muxes are 2 here. There is a mismatch in the number of inputs and the number of select lines. Now we can do, or we can achieve the functionality by short circuiting the S1 and S0, and a common input is taken, that is whenever they are short circuited with each other or whenever they are clubbed with each other, I got a single select line here which is mapped with the A here. And since in the truth table I have only 2 outputs here, with 0 I am getting an output 1, and with 1 I am getting an output 0. Let's see, since A is mapped with the S1 and S0 in a combined manner, if A is 0, then S1 and S0 both will be 0 0. With 0 0, first line is selected, that is D0. As this output is mapped with the D0, D0 is connected to VCC, and with another input combination, that is with A equal to 1, since these two are short circuited, with A equal to 1, S1 and S1 both will become 1 1. With 1 1, the last input data line, that is D3 selected. Since the output has to be mapped here, since the output is 0, this is mapped here. Now I am left with two more input data lines, that is D1 and D2. So since these D1 and D2 are of no use, I can write these as don't care. This is how the functionality is implemented using 4:1 mux. Now we shall see how to implement the logic gates functionalities using 2:1 mux. In the previous case, what we have seen is the number of inputs in the logic gates were equal to the number of select lines in the 4:1 muxes. But here there is a mismatch in the number will be there. You can see here in AND gate it needs 2 input, and in 2:1 mux there is only one select line. Means I cannot directly map the 2 inputs with the select line of the 2:1 mux because there is a mismatch in the number. So AND gate ಗೆ 2 ಇನ್ಪುಟ್ ಇರ್ತವೆ, ಆದರೆ 2:1 ಮಕ್ಸ್ಗೆ ಒಂದೇ ಸೆಲೆಕ್ಟ್ ಲೈನ್ ಇರುತ್ತೆ. ಆದರೆ ಪ್ರೀವಿಯಸ್ ಕೇಸ್ನಲ್ಲಿ ನೋಡಿದಾಗ 4:1 ಮಕ್ಸ್ನಲ್ಲಿ 2 ಸೆಲೆಕ್ಟ್ ಲೈನ್ಸ್ ಇದ್ದಿದ್ದರಿಂದ ಆ ಇನ್ಪುಟ್ಸ್ನ ಡೈರೆಕ್ಟ್ ಆಗಿ ಸೆಲೆಕ್ಟ್ ಲೈನ್ಸ್ ಜೊತೆ ಮ್ಯಾಪ್ ಮಾಡ್ತಿದ್ರಿ. ಬಟ್ ಇಲ್ಲಿ ಆ ಥರ ಮಾಡ್ಲಿಕ್ಕೆ ಬರೋದಿಲ್ಲ. So here we use a special method called as map entered variable method, or simply it is abbreviated as MEV method, that is map entered variable method anta karitare. So here out of 2 inputs, so AND gate andaga enagutte, so this is your AND gate which will have 2 input. One, let's designate one as A, another one as B, and the output is Y here. Either I can map A with the select line, or I can map B with the select line, because out of these two only one can be mapped with the select line, because the number of select lines in the 2:1 mux is only 1. So it is always preferred to map the second input, that is B here, with a select line content, that is S. So B na S jote map madidri. Okay. Whenever one input is mapped with a select line, the leftover input, that is ಯಾವ್ದು ಉಳಿದಿರುತ್ತೋ ಅದನ್ನ ಏನಂತ ಕರಿತೀವಿ ನಾವು MEV ಅಂತ ಕರೀತಾರೆ, that is map entered variable ಅಂತ ಕರೀತಾರೆ. So the inputs of the 2:1 muxes, that is D0 and D1, these are mapped with the A ಜೊತೆ ಇದನ್ನ ಏನು ಮಾಡ್ತಾರೆ, ಮ್ಯಾಪ್ ಮಾಡ್ತಾರೆ. ಯಾವ ಥರ, ಯೂಸಿಂಗ್ ಇಂಪ್ಲಿಮೆಂಟೇಷನ್ ಟೇಬಲ್ ಹಿಯರ್. ಸೊ ಲೆಟ್ಸ್ ರೈಟ್ ದ ಟ್ರೂತ್ ಟೇಬಲ್ ಫಸ್ಟ್. ಸೊ ಆ್ಯಂಡ್ ಗೇಟ್ ಅದು ನಿಮ್ಗೆ ಆಲ್ರೆಡಿ ಟ್ರೂತ್ ಟೇಬಲ್ ಗೊತ್ತು, with 0 0 0, with 0 1 0, with 1 0 0, and with 1 1 again the output is 1 here. So if you write the decimal equivalent of the input combinations, decimal equivalent of the input combinations andre enagutte, this will be 0, this will be 1, this will be 2, and this will be 3. Okay, these are the decimal equivalents of the input combinations. So map entered variable yaudide, A. So you can see here for the first two decimal combinations, that is for the decimal combination 0 and for the decimal combination 1, what is the value of A here? It is 0. Means A can be designated as A bar. For the next two combinations, for the decimal combinations 2 and 3, the value of A is 1, so that I can designate the map entered variable as A here. For the first two combination it is A bar, and for the next two combination it is A. Now the D0 and D1 of the inputs have to be changed, or they have to be mapped with the map entered variable, that is they have to be mapped with A according to the implementation table. How to write the implementation table? Now what have to be changed here? D0 and D1. So adanna row agi barkoboku. So sorry, column agi barkoboku, D0 and D1. Next, according to what these have to be changed? These have to be changed according to the map entered variable A. The possibilities of the map entered variable values andre ಏನಾಗುತ್ತೆ possibilities ಅಂದ್ರೆ A bar and A. So A bar ಯಾವ combination ಗೆ, decimal combination ಗೆ ಯಾವ combination ಗೆ A bar ಅಂತ ಇರುತ್ತೆ? For the decimal combination 0 and 1. Write the decimal combinations 0, next 1. A ಎಲ್ಲೆಲ್ಲಿ ಇರುತ್ತಪ್ಪ 1 ಅಂತ? For the decimal combination 2 and 3. Right, 2 and 3. Okay, now I hope now you have understood how to write this implementation table. The next step is to circle them. ಯಾವುದನ್ನ circle ಮಾಡಬೇಕು? For which combination the output is 1, you have to encircle. You can see here, for the third decimal combination the output is 1, for other cases it is 0. So for whichever case the output is 1, you have to encircle it. ನೀವು ನೋಡಬಹುದು 0 1 2 3. So third decimal combination ಗೆ 1 ಇರೋದ್ರಿಂದ so you will ಇಲ್ಲೊಂದು circle ಹಾಕ್ತೀರಾ. Okay, now it is over. What is the next step? Next step is to add. So add ಮಾಡಬೇಕಾದಾಗ ಏನು ಮಾಡಬೇಕಪ್ಪ ಅಂದ್ರೆ, so whenever a particular combination or whenever a particular decimal combination is not encircled, circle ಹಾಕಿಲ್ಲಪ್ಪ ಅಂದ್ರೆ its value is considered to be 0. And if it is encircled or if it is circled ಅಂದ್ರೆ ಅದನ್ನ circle ಹಾಕಿದ್ರಪ್ಪ ಅಂದ್ರೆ you have to consider its row value. ಅಂದ್ರೆ ನೀವು ನೋಡಬೇಕಾಗತ್ತೆ ಇಲ್ಲಿ ಫಸ್ಟ್ ಇವೆರಡನ್ನ ಆ್ಯಡ್ ಮಾಡಬೇಕಾದಾಗ ಕಾಲಮ್ ವೈಸ್ ಆ್ಯಡ್ ಮಾಡಬೇಕಾದಾಗ 0ನು ಸರ್ಕಲ್ ಆಗಿಲ್ಲ, 2ಗೂ ಸರ್ಕಲ್ ಹಾಕಿಲ್ಲ, ಅಂದ್ರೆ ಇದ್ರ ವ್ಯಾಲ್ಯೂನು 0 ಆಯಿತು, ಇದ್ರ ವ್ಯಾಲ್ಯೂನು 0 ಆಯಿತು. 0 ಪ್ಲಸ್ 0 ಅಂದ್ರೆ ಏನಾಯಿತು? 0. ಅಂದ್ರೆ D0 is mapped with 0. ನೆಕ್ಸ್ಟ್ ಇಲ್ಲಿ ಕಾಲಮ್ ಸಮ್ ಮಾಡಬೇಕಾದಾಗ 1 ಅನ್ನ ಸರ್ಕಲ್ ಹಾಕಿಲ್ಲ, ಬಟ್ 3 ಅನ್ನೋ ಡೆಸಿಮಲ್ ಇದಕ್ಕೆ ನೋಟೇಷನ್ಗೆ ಒಂದು ಸರ್ಕಲ್ ಹಾಕಿದೀವಿ. ಸರ್ಕಲ್ ಹಾಕಿದ್ರೆ ಯಾವ ಟು ಕನ್ಸಿಡರ್ ದಿ ರೋ ವ್ಯಾಲ್ಯೂ. ರೋ ವ್ಯಾಲ್ಯೂ ಅಂದ್ರೆ ಏನಾಯ್ತದು? ಎ. ಇದಕ್ಕೆ ಸರ್ಕಲ್ ಹಾಕಿಲ್ಲಪ್ಪ ಅಂದ್ರೆ ಇದನ್ನ ಏನಂತ ತಿಳ್ಕೋಬೇಕು? 0. 0 ಪ್ಲಸ್ ಎ. ಆಸ್ ಪರ್ ಬೂಲಿಯನ್ ಲಾಸ್ ಯು ಕ್ಯಾನ್ ಸೇ 0 ಪ್ಲಸ್ ಎ ಮೀನ್ಸ್ ಎ. D1 is mapped with A. So as per this implementation table, D0 should be connected to 0 and D1 should be connected to A. D0 is connected to 0 and D1 is connected to A. Understood? Let's see whether it works as per the truth table or not. With 0 0, with A 0 and B 0. A kuda ಏನಿರುತ್ತೆ? 0 and B also is 0. With 0 0. So with select line 0, D0 is selected. D0 select ಆಯ್ತಪ್ಪ ಅಂದ್ರೆ D0, what is the content of D0? 0. So output Y will be equal to 0. The first combination is verified. Second combination, with A equal to 0 and B equal to 1. A let it be 0 only and B equal to 1. With B equal to 1 means with select line content equal to 1, second line that is D1 is selected, which is A and which is again a value 0, means 0 is routed to output Y. So second combination is verified. The third combination with A equal to 1 and B equal to 0. Andre A equal to, now it is 1 and B is equal to 0. With B equal to 0, first line is selected. Again its value is 0. It appears across the output line Y, means the third combination is also verified. And finally with both A and B with the values 1 and 1, ಸೊ ಬಿ ಕೂಡ 1, ಎ ಕೂಡ 1. ಹಂಗಿದ್ದಾಗ with select line 1, second line is selected. What is the content of A? 1. 1 will appear across output line Y, means the fourth combination is also verified. Like this, successfully the AND gates functionality is implemented using map entered variable method. Second case, OR gate. First we shall write the truth table and we will map the one of the inputs. Usually the second input, that is B, is mapped with the select line. ಇಲ್ಲಿ B ಜೊತೆ ಮ್ಯಾಪ್ ಮಾಡಿದಿರಾ. So we are left with one more input, that is A. Now the inputs D0 and D1 have to be modified according to the implementation table here. Map entered variable ಯಾವ್ದಪ್ಪ ಈಗ A ಅಂತ ತಗೋಬೇಕು. Possibilities of A, ಏನೇನಿರ್ಬೋದು possibilities of A? For the first two combination it is 0 and for the next two combination it is 1. So write it 0, 1, 2, 3. Now after writing these, next step is to circle them. So whenever we got 1, ಅಂದ್ರೆ ಯಾವ ಕಾಂಬಿನೇಷನ್ಗೆ 1 ಅಂತ ಬಂದಿರುತ್ತೋ ಆ ಕಾಂಬಿನೇಷನ್ಗೆ ಏನು ಮಾಡಬೇಕು, ಸರ್ಕಲ್ ಹಾಕಬೇಕು. ಅಂದ್ರೆ ಫಾರ್ ದ ಡೆಸಿಮಲ್ ಕಾಂಬಿನೇಷನ್ 1, 2 and 3 we have got an output 1. ಇಲ್ಲಿ ಸರ್ಕಲ್ ಮಾಡಿದ್ವಿ, ಇದು ಸರ್ಕಲ್, ಇದು ಸರ್ಕಲ್, 3 ಸರ್ಕಲ್ ಮಾಡಿದ್ವಿ. What is the next step? Next step is to add them column wise. So suppose it is not circled, means its value is considered as 0. So suppose it is circled, means we have to consider the value row value. Andre 0 plus A anta bantu. Now these two are circled. Andre the value of this one is A bar and the value of this one is A. A bar plus A, as per the boolean law, it is 1. Means D0 should be connected to A and D1 should be connected to 1, that is VCC. And if you verify as per the truth table, we will get the same functionality of the OR gate using 2 stone mux. Okay. Similarly, NAND gate, B is selected as B is connected to select line of the 2 stone mux, and again here also A is treated as map entered variable. We write the implementation table. The D0 and D1 are modified according to the implementation table here. You can see here for the first two combinations it is A bar. For the next two combination it is A. We write the decimal equivalent of the input combinations, that is 0, 1 and 2, 3. So for the first three combinations it is 1 and for the last decimal combination it is 0. Next ಏನು ಮಾಡಬೇಕು, circle ಮಾಡಬೇಕು. After that now we have to add in the column wise. So since these two are circled ಮಾಡಿದಾಗ ರೋ ವ್ಯಾಲ್ಯೂನ ಕನ್ಸಿಡರ್ ಮಾಡಬೇಕಾಗುತ್ತೆ. A bar plus A, that is 1, and this is A bar. Since this one is not circled, it is considered as 0. A bar plus 0, A bar. D0 is mapped with 1 and D1 is mapped with A bar. This is how NAND gate is implemented. Similarly, NOR gate, B is connected to select line and A is treated as map entered variable, and as per the implementation table we will modify the D0 and D1 contents. Once we do all the steps whatever we have done in the previous case, we get D0 equal to A bar and D1 equal to 0. So D0 is connected to A bar and D1 is connected to 0. Similarly, XOR gate, and XNOR gate. Here also, in these two cases also, B is connected to select line and D1 and D0 are modified according to the map entered variable content as per the implementation table. Finally, NOT gate. In case of NOT gate, this is a special case again. In NOT gate, we will find only one input, and 2 is to in 2 is to 1 boxes also we will find only one select line. Means, as we discussed in the previous method, that is using 4 is to 1 mux, the number of select lines and the number of inputs of the gates were equal. Here also, in the same sense, here also the number of inputs of NOT gate is 1 and the number of select line of the 2 is to 1 mux is also 1. I can directly map the input A with a select line S here, with a select line S here, and the outputs are mapped with the inputs. Means 1 is mapped with D0 and 0 is mapped with D1. You can consider with A equal to 0, the select line will become 0 here. Since the select line is 0, it selects the first data input na select ಮಾಡುತ್ತಾ, which is connected to 1 or VCC. So 1, it will appear across the output line Y. First combination is verified. Similarly, with A equal to 1, second line is selected, which is connected to 0. 0 will appear across the output line Y. Second combination kuda verify ಆಯಿತು. Okay. The brief summary is here is, whenever we have the number of inputs of the gates and the number of select lines for a particular mux are equal, then we directly map the inputs of the logic gates with the select lines of the mux, and as per the truth table we will map the outputs of the logic gates with the inputs of the multiplexers. So which we have seen while using 4 is to 1 mux. And in the second case, what we have seen is, since the number of inputs of the logic gates and the number of select lines of the multiplexers are not equal, then we use a special method called as map entered variable method. So there, out of two inputs, one of the input, usually the second input of the gate, is mapped with the select line, and the inputs of the multiplexers are modified according to the implementation table. Okay, thank you.